Hello, ladies and gentlemen. Welcome to Wednesday. I hope you're doing well. So today, instead of covering anything new and instead of giving you a quiz, I decided that we're going to do some review. So we've covered four important concepts recently. We've done molarity, molality, freezing point depression, and boiling point elevation. So I've written up 8 problems. Um, I'm going to do 4 of them, one of each, and then I'm going to let you do the other 4 for homework. I'm not requiring you to take notes today, so I don't need a picture of your notes, but I would recommend you take them anyway, just so you have more examples. Because I'm going to do 4, then you're going to do 4, and then your quiz is going to be 4. So it'll be important that you kind of get the ideas how to do it. If you have questions, today is the day to ask them on the GroupMe or via text. You guys have my GroupMe and you have my phone number. But with that being said, let's get started. I started recording the video and I was doing number 1, but then I just changed my mind and I realized I want to do number 2 instead. So, you guys will do number 1. I will do number 2. You have 0.75 liters of a 0.8 molar hydrofluoric solution. How many moles of HF do you have? Okay, so what is my formula? Molarity equals moles over liters. What can I plug into this equation given what I have? Because I know that it's supposed to be the solute in the solution. Well, I have 0.75 liters of a 0.8 molar. Do I have any moles right now? That's capital M and that's liters. I don't have moles, but I do have my M and I do have my L. So just like in math, I'm going to just plug these numbers in. So my M is 0.8 equals moles, which I don't have, over liters, which I do have. Okay? Now, how do I solve for moles? Well, how do I get 0.75 liters out of the denominator? It looks like I have to multiply both sides by 0.75 liters. Oh, that was silly of me to do. Okay, now these cancel out, and these are multiplied together, so I'm left with 0.75 liters times 0.8 molar equals moles. Now, what's 0.75 liters times 0.8 molar? That equals 0.6 moles. 0.6 moles of what? Of HF. And that's my answer. So this one is more of just a plug and play. Now for number 1, a hint is that this is not in the correct units right now. You will need to deal with that. That's as complicated as molarity is going to get. Now, molality, which one of these do I want to do? Oh, they're both kind of done the same way. I'll do number 4 just to keep it consistent. A puddle is a mixture of 2.95 kilograms of ethylene glycol, which is 2 carbons, 6 hydrogens, and 2 oxygens. And that is in 7.75 kilograms of water. What's the molality? And I hope I would know your answer to should you drink it. So what's my equation for molality? It's little m equals moles per kilogram. And again, that is solute in solution. So which one of these is going to be in the other one? Well, it definitely looks like this is in that. So it kind of gave me the answer there. So I'm going to put 2.95 kilograms of C2H6O2 over 7.75 kilograms of water. Now what is it asking for? The molality. For molality, I need it to be moles per kilogram. Is it in that unit right now? Well, the bottom one is. It looks like the bottom one's fine. It's kilograms already. The top one is not fine. This is not in moles, so this is going to need to be in moles. So let's think real quick. How do I get something into moles from grams? Well, remember when we were doing our liter to gram, I'm sorry, when we were doing our liter, oh my gosh, when we were doing our gram to mole to liter conversions, from gram to mole we had to use the weight, right? The atomic weight. So it looks like we're probably going to have to do the same thing here. But the problem is, that's going from grams to moles, right? Not kilograms to moles. So if we need to get to moles, we also have to go to grams. So if I want to turn kilograms into grams, how many grams are in 1 kilogram? I'm going to have to multiply this by 1,000 grams. So that way, my kilograms cancel out. Okay? So now my top is in grams. So now I can go from grams to moles. So if I want to go to moles, 1 mole of C2H6O2, how many grams are in 1 mole of that mess? Well, I looked at the periodic table and I added it all up for you. It is 62.07 grams of C2H6O2. So my grams cancel out. These C2H6O2s cancel out. So all I'm left with in the top is 2.95 times 1,000 times 1. And all I'm left at the bottom is 7.75 times 1 times 62.05. Now when you plug all these numbers into the calculator, you end up with 6.13 molol. And that is your answer. Number 3 is done super similarly. Um, so just remember that you need moles over kilograms. And what do you have as units? There's your hint. So now let's talk about boiling point and freezing point. Okay, so before we do the boiling point and freezing point, I think it's time we address the elephant in the room. What the heck is going on when we divide or multiply by the number of elements in our compound? So on page 322, there's this great paragraph I'm going to read you. Recall that ionic solutes produce more particles in a solution than covalent compounds do. When a covalent compound dissolves, it separates into molecules, big chunks, but ionic compounds dissociate to form 2 or more ions per formula unit. Thus, the number of particles or moles must be multiplied by the number of released ions per formula unit when you calculate the impact of molality on boiling points. This result is referred to as the particle molality of a substance. Now, that's a really fancy and complicated way of saying when you have an ionic bond that's being broken up, you're going to need to multiply by the number of atoms. But when you have a covalent bond, you're not going to need to do that. Now, how do you figure out whether or not you're dealing with an ionic or a covalent? Well, here's a pretty simple trick. So look at this 12-8. Look at these two elements. You have acetone, which is carbon, hydrogen, and oxygen, and then you've got naphthylamine, which is C and H. Where on the periodic table are CH and O? Well, C and O are both over here, right? And I think you'd agree that neither of these are super strong. They're not as strong as these. And then you got H, which is super weak. So you got a lot of H's and C's. And H's and C's, neither of those are really strong. So that you can kind of guess would be a covalent bond. Now, when you start talking about ionic, let's say NaCl. Na is over here, and then Cl is on the complete opposite side. That's usually going to be an ionic when you're including one of these things because it's strong. Additionally, when you have a metal somewhere in the middle, a middle metal, sorry, I don't even know why that was funny, or one of these down here, that's usually going to be ionic as well. So if you're just dealing with a bunch of C's and H's, that's when you can pretty much decide that this is not going to need to multiply by the M. Now, when you have one of these stronger ones, you probably are. So with that being said, let's get back into it. So first I'm going to do a problem for boiling point that is covalent, and then I'm going to do one that is ionic. So here's the covalent one. I'm going to do number 5. What is the boiling point for ethanol when 3.2 moles of naphthalene is added to 2 kilograms of ethanol? And then I give you the boiling point and the kb. I'm getting those two numbers from page 322, which you're going to need to get for number 6. So what is my equation for boiling point elevation? It's the change in boiling point equals the molal boiling point elevation constant times the molality. And I know molality is moles per kilograms. So what am I given? I have the Kb for ethanol, so I can go ahead and plug that in. Do I have the change in temperature? No, doesn't look like I do. So my change in temperature equals my constant, which it looks like is 1.22 degrees Celsius molal times something. What is my molality? So I have moles and kilograms in this equation, so it looks like I can just plug those in. Molality equals moles per kilogram, so that would be 3.2 moles per 2 kilograms. And if I were to simplify 3.2 over 2, that would give me, I should have done this in advance, but I didn't, 3.2 over 2, that would give me 1.6 m. So I'm going to plug 1.6 m into this equation. My two m's are going to cancel out when I multiply this. So the question is, what's 1.6 times 1.22? So funny you should ask. It's 1.95. So I get 1.95 degrees Celsius as my answer. Now, is it asking for my change in boiling point? No, it's asking for the boiling point. So if I changed this much, what was the original? Well, that's in the book. The boiling point of ethanol is 78.26 degrees. So I had 78.26 degrees Celsius originally, and I'm increasing it by 1.95 degrees Celsius. And that's going to give me my final answer, which I'm not going to calculate for you because I'm sure you can put that in your calculator. So that's how you do standard boiling point elevation equation. Just plugging numbers in interpreting. So you please do number 6. Now let's try one that has to do with an ionic bond. Okay, so ionic boiling point problems. Number 7 and number 8. I'm going to do number 7. You'll do number 8. So how do we know this is an ionic problem? Well, we look at magnesium and fluoride. That fluorine is a really powerful ion. And then we have magnesium, which is way on the other side. So this isn't carbons and hydrogens. This isn't weak sauce. This is strong stuff. And so we can assume that this is going to need to be doing that janky little um, multiplication thing. So when I do this, what is my boiling point formula? It's the change in boiling point equals the boiling point constant times the molality, right? So what do I have in the problem? Well, what is my bigger thing, right? My bigger thing is water. So what I'm going to be needing is the boiling point constant for water, which luckily for us is right in the book, and it should be in your notes. 0.512 degrees Celsius over molality. So I'm already almost done. I just need my molality. Do I have my molality? It's not written anywhere, so I need to find it. So what's my equation for molality? It's moles per kilogram. And like I keep saying, that also means the amount of solute in your solution. So do I have any moles? Nope. Do I have any kilograms? Nope. So I'm going to have to just put my solute where it belongs, my solution where it belongs, and figure out how things work as I go. So what is in what? It looks like the magnesium fluoride is being put into the water. I have more water, so that's my solution. So that gives me 430 grams of magnesium fluoride over 700 grams of water. So, what is my boiling point? I need to figure out how to get this into the form of molality so then I can plug that answer in right here. So, my denominator is not in kilograms. That's the easiest thing to take care of. So if I want this to be kilograms, then I need to multiply by 1 kilogram. And how do I convert from grams to kilograms? I divide by 1,000 grams. Perfect. Okay, so that makes my grams of water cancel. So now I have kilograms of water in the denominator. Perfect, that's exactly what I wanted. So now how do I get moles in the top? How do I convert from grams of magnesium fluoride to moles of magnesium fluoride? Well, I multiply by 1 mole of magnesium fluoride, and I divide by the molar weight. And if I add up all the weights for magnesium and 2 fluorides, I already did that for you, it's going to be 62.30 grams. So, I have moles per kilogram now, and that's exactly what I want. But this is when we add in that janky last step. So, how many different pieces do I have? Because this magnesium and these fluorides are going to break apart into an Mg, an F, and an F. How many things do I have in total? 3. So I'm going to have to multiply this by 3 up here too. I think it'll be easier to do while you're already multiplying, so then you don't have anything confuse you. So for ionic problems, when you get to moles per kilogram in the molality, then you're going to end up multiplying by the amount of pieces you have. So when we multiply all this out, and I don't think I already did this because I'm lame, you end up with 430 times 1000 times 1 times 3, and then that is divided by 700, and it's also divided by 62.30. And you end up with 29.58 molal. So now that I have that, I can plug it into my equation, because that's what I needed. I needed the 29.58 molal. Now when I multiply these, my two m's will cancel out, and all I have to do is multiply by 29.58 times 0.512, and I got 15.15, and then that degrees Celsius is my unit. Hooray! 15.15 degrees Celsius. Now what did the problem ask for? What's the boiling point? It didn't ask me for the change in boiling point. So now that I have the change, I need to combine this with the standard boiling point. And the standard boiling point is going to be 100 degrees Celsius. So 100 degrees Celsius plus 15.15 degrees Celsius is going to give me, drum roll please, 115.15 degrees Celsius. That is my final answer. Now you just have to do the exact same thing with number 8. Now, I'm not going to make you do a freezing point depression problem thinking about it, because the boiling point and the freezing point problems are done exactly the same. The only difference is going to be that you'll use KB or KF instead of KB, and the change in freezing point temperature instead of the change in boiling point temperature. So Let's just do these problems. So that leaves you with one ionic problem. Where's my page? One ionic problem, um, one standard boiling point problem, one molarity problem, and one molality problem. So that's four problems. So if you could do those, again, I'm not asking you to take notes today. All I want you to do is send me a picture of your answers for that and your work. I need your work. Um, and I also need you to ask questions if you don't understand it. Hopefully that cleared up the whole multiplication division problem thing. Um, and with that being said, I wish you guys a good luck. I'm praying for y'all, and have a good day.